Right, so we are in the middle of discussing group actions. We went over some examples. But to start off today's lesson, let me go over the definition of a group action real quick as a small recap. Mm. Group action on a set. Okay, so the definition tells you if you have a set X and a group G, G acts on X in a certain way. Let me first write G a group, X a non-empty set, any set. So the group action, which we will define as phi, is a function this to X such that it satisfies, first of all, the identity, or in other words, phi of E comma X, any element that you take from this set X, which we summarized to being E dot X, right? Where E dot X, this dot refers to the group action now, E is equal to X for all X in the set. And the second condition being G1, G2 dot X equals G1 dot G2 dot X. For every G1, G2 that you take from the group and any element X. Okay, so we were actually discussing. Right. This is the last example which we couldn't finish. Let's take G to be a group. And let's take H to be a subgroup of G. We take G to be a group and H a subgroup of G. Then by L sub H, let's define L sub H to be the set of all left cosets of H in G. So this will contain all the elements of the form. This. Now remember, H is simply a subgroup of G. So this will contain all left cosets of H in G. Right? So in this case, we say that LH is a G set. In other words, the group G acts on this set, and the group action, we define it in this way. And we define the group action phi from G cross L sub H to LH by G dot, G comma X H. G taken from the group, XH is any left coset of H in G. This to be simply defined by the notation that we agreed to, G dot XH, to simply be GXH. In other words, these two elements will be mapped to the left coset of H in G by the element GX, because now this G is taken from G. XH is a left coset of H in G. Therefore, this representative, this element that you see over here, X is also taken from G by definition. So GX, this product that you see over here, is an element in G. Right? So let's see whether this satisfies the given properties for a group action. First of all, we have to take the identity of G, which we usually denote by E. So let's see whether the first property is satisfied. That is phi of the identity times any element that you take from L sub H. This, by definition of this mapping, is given by identity times X H. And identity times any element in the group, by definition of the identity, is simply XH. So the first condition is satisfied. This is for all XH in LH. Now the second condition, let's take G1, G2, and X all to be in G, so that XH is an element in L sub H. Now, let's find phi of G1, G2, comma XH. This, by definition of this group action, is given by G1, G2 times X, H. Now, this you can write as G1 times G2X, H. We are simply using the associative property of the binary operation defined on G. And this, if you apply this, the group action, we see that this is simply G1 times phi of G2 X H. This is equal to, if you go back to the definition, this is simply equal to phi of G1 comma phi of G2 X H. Right. Why do we have this? Observe that phi of G2 comma XH is an element in the set L sub H. It's an element, or it's because this function phi is from G cross LH to LH. So what you get over here is a left coset of H in G, right? So you take G1 dot this element by definition. If you go over here by definition, this is simply phi of G1 times that element in L sub H. So the second condition is also satisfied. Therefore, we see that this is indeed a group action. Okay. Let's go to the definition now, a new definition. Let's take X to be, now we are going to define the stabilizer of any element that you take from this, from a set X, which is a G set, right? So let X be a G set. In other words, G is a group acting on X. And an element X taken from this set be fixed. So for a fixed element, we are defining this set. The stabilizer of X is defined to be usually define it by step X, the set containing all elements in G such that G dot X equals X. In other words, every element in G that fixes X through this group action, right? Once you take the element G in G, and for this particular X, through this group action, because X is a G set, the element will be fixed. If that is the case, this G will belong in this set, which we call the stabilizer of X. Right. So next theorem, we see that now observe for any element that you take, once you fix the element that's in the set X, you define it to be every element in G, you define the stabilizer of X to be every element in G that fixes this X through the group action. So this is a subgroup of G, not just a subgroup. Yes, it's what I wanted to say was it's a subset of G, not just a subset, but also a subgroup. So that is the next theorem. We will show that it's a subgroup of G. The stabilizer for this fixed X that we defined over here is a subgroup of G. Right. So to prove, we will simply use the subgroup criterion. So the first thing is we have to show that this is not empty. This is not empty. How do we conclude that? How do we show that this is not empty? We have to show that there is at least one element. Can you give me a specific element that's in this set?
The identity element
The
E dot
identity
X.
element. Yes, very good. Why is that? From that,
E dot X is equal to X by the properties of the group action.
exactly. For any X, for every X, we will always have the identity dot X to equal X. So the identity element will always be in the stabilizer for any element that you fix in X. So we simply can write this is not empty since the identity is an element in stab X as E dot X is equal to X for every X that you take from the set. Now, the next would be to pick any two elements from this set, the stabilizer of X. Let's take them to be G1, G2. And first, let me write clearly this is a subset of G. As you can see, we take elements of G from G that fixes X, right? So it's clearly a subset of G. All we've got to do is to show that it satisfies that subgroup criterion, right? So let's pick any two elements. Let G1, G2 be two elements that you take from the set stab X. Because these two are taken from the set stab X, we know that they have to satisfy the given condition of the set. In other words, they must fix the element X, right? Then we must have G1 dot X to equal X and G2 dot X to equal X, right? Now observe G2 dot X is equal to X, right? This implies that G2 inverse dot X is also equal to X. Why do we have this? Why do we have this to be true? G2 inverse dot X is equal to X. What we can do to see that, now observe, we have taken the two elements G1, G2 from this set to use the subgroup criterion. What do we do when we say we are going to use the subgroup criterion? We have to show that G1, G2 inverse is also an element in this set. In other words, G1 times G2 inverse must fix this element. So we have to incorporate G2 inverse somehow into our equation, right? So now we have G2 dot X to equal X. What do we do now? G2 dot X is an element in the set X. So we take the group action, or we consider this group action over that element G2 dot X and G2 inverse. So what we do is simply consider this, take G2 inverse on both sides, dot G2 dot X equals G2 inverse dot X, right? Now this implies we simply use on the left-hand side of our equation, the second condition of that group action. What do we have? We have G2 inverse G2 dot X equals G2 inverse dot X. G2 inverse times G2 is simply the identity. Identity, which is E dot X is simply X. So we have this element to be E dot X, which is equal to X, and what we see on our right-hand side. Okay, so if G2 is in the stabilizer of X, G2 inverse, the inverse element also is in there. Okay, now we will show that we will show that G1, G2 inverse is also an element in stab X. So how do we show that this element actually belongs in this set? By showing that it also fixes this particular element X. So let's take G1, G2 inverse dot X. This is equal to, by that second condition of a group action, G1 dot G2 inverse dot X. This is equal to G1 dot, and we know that from here, G2 inverse, from this above statement, G2 inverse dot X is simply equal to X. So we will simply replace this term by X. And because G1 belongs in the set stab X, this also fixes X. And from this equation, G1 dot X equals X, we know this is equal to X. In other words, we've got G1, G2 inverse dot X to equal X. G1, G2 inverse fixes this element X, right? Therefore, by definition of the set stab X, we see that G1, G2 inverse belongs in stab X. And so, by the subgroup criterion, we have stab X to be a subgroup of G. Right. Do we have any questions?
No.
Okay. Right. So the next is orbits. Orbits. Right. So first of all, let me state this theorem. We are going to define an equivalence relation, and the equivalence class we will define as the orbit. Before we get to that part, let's go over this theorem. Let X be a G set. In other words, you have a group G which is acting on a set X. Right? For X1, X2, elements that you take from X, X1 is equivalent to X2, right? If and only if, if and only if there exists an element G in the group such that G1x1 is, Gx1 is equal to x2, then this tilde, this equivalence, is an equivalence relation on X. This is an equivalence relation on X. Right. So how do we prove that this given relation is an equivalence relation, that this tilde is an equivalence relation? You have to show that this is reflexive. That means for any element X that you take from the set X, X is equivalent to itself, or X tilde X. Then you have to show that this is symmetric. That means if you have x1 to be equivalent to x2, then x2 is also equivalent to x1. x1 tilde x2, then we must have x2 tilde x1. And then the transitive property, right? Then you have to show that this is transitive. Okay, first of all, we will show that this is reflexive. Right? That is x tilde x. Right? Now, how do we show that x is equivalent to itself? How do we show that? We have to give a particular g, right? Such that gx is equal to itself. You have to find some element in the group that will fix x. Okay, if you go over the equivalence relation that's given over here, you have a group G acting on a set X, and we define a relation between any two elements x1, x2, if and only if there exists some element in the group G such that that element times x1 is equal to x2. When I say times, I'm actually referring to the group action. So let me put dot over here. G dot x1, which we will simply write as gx1. Okay. Can we find a specific element in the group that would fix the element x?
Yes, madam.
Which is that element? What is that element?
The identity.
Exactly, the identity element, right? E is in G and E dot x is equal to x for all x in this set. Therefore, by the way we have defined this tilde, we have x to be equivalent to itself, x tilde x. Right. The other one is tilde is symmetric. What does it mean? That means x1 tilde x2, x1 equivalent to x2 implies x2 is equivalent to x1, right? So let's suppose, first of all, x1 is equivalent to x2 under this given tilde. Suppose x1 tilde x2. Because x1 is equivalent to x2, we must have at least one element g, right? Such that gx1 is equal to x2. Then for some element g in the group, we have gx1 equal to x2, right? Now we have to find through this relation a particular g, a particular element in the group such that that element dot x2 is equal to x1. Can we find such element? Is there an element that you can take from the group, say an element G1 such that G1 x2 is equal to x1?
Yes, ma'am.
Sorry?
Ma'am.
Can you say that again?
G inverse, ma'am.
G inverse, exactly. We can take G inverse as in the previous case, right? Previously also we saw that here. When you have G2 dot x equal x, you take G2 inverse on both sides, you end up with the same thing. Not the same thing, I'm sorry. G2 inverse dot x equals x. This is the work, right? So we do the same over here. We take G inverse dot gx1 on both sides so that at the end we get G inverse x2, which is simply G inverse dot x2. I'm excluding the dot over here. This is equal to G inverse G dot x1. G inverse G is the identity. Identity dot x1 is simply x1. Right? Therefore, by definition, we have x2 to be equivalent to x1. So that is also this tilde is symmetric. Last one, we have to show that this is transitive. What does it mean? If you have x1 tilde x2 and x2 tilde x3, we must have x1 to be equivalent to x3. This is what we have to show. So let's first of all suppose that x1 is equivalent to x2 and x2 is equivalent to x3, right? Then by definition of this tilde, we have two elements G1, G2 in the group such that G1 x1 is equal to x2 and G2 x2 is equal to x3. Now we have to find some element in G, let's take it to be simple G, such that Gx1 is equal to x3, right? We have to find that. Now observe, if we start off with this first equation, we've got G1 x1, which is actually G1 dot x1, okay, equals x2. Over here, what I'm going to do is, I will take G2 on both sides. So we've got G2, G1 x1, G2 x2, sorry, equal to this. This implies G2 G1 x1 equal G2 x2. And we know from the second equation, G2 x2 is simply x3. Because G1, G2 are, these two elements are in G, their product is also in G. We have, by definition of tilde, x1 to be equivalent to x3. Therefore, by definition of an equivalence relation, this given tilde, this relation, is an equivalence relation. Is an equivalence relation. Right. Now we know that this is an equivalence relation. We will define the equivalence class, right? In the usual notation, if this denotes the equivalence class. Of some element x in X, right? Then what sort of elements does it contain? This will contain all elements in X that are equivalent to this given representative simple X. In other words, all y in the set X such that X is equivalent to y. All elements that are equivalent to this. So remember that this X is simply a representative in this set. Okay. So if you elaborate this definition, we've got y in X such that under this tilde, how do we say that X is equivalent to Y? When there is some G in the group such that Gx is equal to Y. Right? In other words, this contains every element. Now observe, this y is equal to g dot x. So this y over here, I will simply replace by g dot x. I will write as g dot x in X, where G is an element in the group. This equivalence class is what we call the orbit in X under G. This is what we call the orbit in X under G. Let me give the formal definition. The orbit of an element, the orbit of an element X in this set is the subset G sub X, or we simply denote it by orb X, which is given by G dot X, where G is an element in G. Now observe, this is a subset of X, whereas the stabilizer of X is a subset of G. The orbit of this element, the stabilizer and the orbit, they are all defined for fixed elements in X. So the stabilizer is a subset of G, whereas the orbit is a subset of X, right? So what you see over here, this is as seen, this orbit is seen as an equivalence class in that equivalence, under that equivalence relation tilde, which we defined earlier, right? Okay, so some properties, let me write. We have, once you take all these orbits, all these distinct orbits, let me put it that way, because say you have x1, x2 both to belong in one orbit, both to belong in one equivalence class, right? Then so that basically means they are in the same orbit, right? They are in the same orbit. So what we do is for each element, we find all these orbits and we take all the distinct orbits, right? The union of all these distinct orbits must give you X by properties of equivalence classes, right? If you have two different elements in one equivalence class, if you take those representatives and find the equivalence classes separately, like I told you for X and Y, which are in the same equivalence class, you get the same equivalence class. So what we do is we find distinct equivalence classes, and we know that The union of all those will give you back the set X, right? So let me write over here, X will simply be the union of all these orbits. Let me put it as X I, right? Now, if G is a finite group, then we have a finite number of elements in G, right? In that case, we have a finite number of orbits. When G is a finite group, so we have a finite number of, let's say, orbits, finite number of distinct orbits, and orb x1, orb x2, likewise we have up to orb xn. And this is a partition of X. It's a partition of X. Right. And the other thing is, now observe that X is the union of all these orbits. So any element that you take from this set will be contained in at least one orbit, right? And not only that, because these orbits are equivalence classes under that equivalence relation given by tilde, any two orbits will always either be identical or disjoint. They will always either be identical or disjoint. Let me write that one also as a small remark. Any element is contained in at least one orbit and two orbits, any two orbits that you pick are either disjoint or identical. Either disjoint or identical. Okay, let's go over one example. Let's consider the group S3. This has elements, all these permutations of the set X containing elements 1, 2, 3. So all these functions, we have the identity, then we have 1, 2, this the permutation given by this cycle decomposition, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. Yeah, this is all, right? Now, first of all, we have to define, this is the group. What we are going to do is we will define the action, or we will consider the action on of S3 on itself by conjugation. So let me write consider the action of S3 on itself by conjugation. That means we have G dot X to simply be Gx, G inverse. We did this example last time, right? For all Gx that you take from S3. Now remember, this group action is, now S3 is acting on itself by conjugation. So when you define this map, it is from S3 cross S3 to S3 given by phi of Gx, which is simply going to be written as G dot X, Gx by Gx, G inverse, which is what we call conjugation. Okay. Now, let's find, if you calculate the stabilize of the element 1, 3, right? Now we are going to pick an element in this set. So because the group is acting on itself, I will simply refer to it as just the group because it is the group. An element on the element 1, 2 in S3. Let's find the stabilize of this element 1, 2. By definition, this contains every element in the group where uh, these elements fix the element 1, 2 by the group action. So in other words, we must have G dot 1, 2 to equal 1, 2. 1, 2 must be fixed by this group action when taken with the element simple G. So for every element, we will do this. We surely know this contains the identity, right? Because the identity dot uh, any other element in the set in this group will give you the element by definition of the group action. Right. Let's take to see what elements we have in there. We surely know this contains the identity. Let's see whether 1, 2, which is also an element in S3, is in this set. Right? How do we do that? We find 1, 2 dot 1, 2. This is given by 1, 2. If you apply this group action, G is 1, 2. X is also 1, 2 now. Times 1, 2. Times 1, 2 inverse. What is the inverse of 1, 2? 1, 2 itself. Right? The inverse is also itself. We simply write when all these permutations are given in the cycle decomposition, we start with this last element and we write it down first and go in that direction from right to left. So we get the same element in this case 1, 2. We have 1, 2 times the identity and simply 1, 2. Observe that 1, 2 dot 1, 2 gives you the same element. Therefore, 1, 2 fixes itself, right? This belongs in its stabilize as well. Do we have any other elements? If we check 1, 3, if you go with 1, 3 dot 1, 2, this is simply 1, 3. 1, 2, inverse of 1, 3. Inverse of 1, 3 is also 1, 3 itself, right? This gives you, if you calculate these to 1, 3 times 1, 2, you see that this is 1 goes to 2 and 2 goes to 2. So 1 goes to 2, 2 goes to 1, 1 goes to 3. This is actually 1, 2, 3 times 1, 3. If you calculate this permutation, this product, you see this ends up being 2, 3, which is not equal to 1, 2. Therefore, 1, 2 will not be fixed by the element 1, 3. So 1, 3 does not belong in the stabilizer, right? And if you do this for 2, 3 also, you see this will not equal 1, 2. 2, 3 will also not belong in, 2, 3 will also not fix 1, 2 through this group action. And do this for every other element to see that the stabilizer only contains these two elements. The stabilizer will only contain these two elements. Right, now let's find the orbit of 1, 2. Which is usually given by G sub 1, 2, or we can write orb of 1, 2. What sort of elements do we have here? We simply take the action on this element by every element in the group. So we take all elements in the group G dot 1, 2. right? Then where G is in S3. This definitely has 1, 2, because when you take the identity times 1, 2, identity dot 1, 2 simply is 1, 2, right? So it is in there. When you take 1, 2, as we have seen over here, 1, 2 dot 1, 2 is equal to 1, 2. So 1, 2 is in there. By the identity also we see that. Then we have 1, 3 dot 1, 2. This is equal to 2, 3. Therefore, 2, 3 element is also in there. Right. And then let's find 2, 3.12 is actually this element gives you can do the calculations and see 1, 3. So we have 1, 3. And these are the distinct elements. Now we obviously have to find 1, 2, 3.12 and 132.12. And these are the only three distinct elements that you get in the orbit. So the orbit of 1, 2 contains these three elements. Okay, these calculations you can do on your own and make sure. Uh, any question? Okay. Okay, now with this we go to the orbit stabilizer theorem. Okay, let me state the theorem first. The number of elements in the orbit of this element x is equal to the index given over here of step x in G, right? So if I simply write it, this means the number of elements, order of orb x is simply equal to this index. But what does this index give you? It gives you the number of left corsets of step x in G, right? Yeah, x is an element in the set x. Right. In particular, when G is finite, we can simply say that the order of this orbit of x divides the order of the group G, right? So let me write in particular. If G is a finite group, then the number of elements in any orbit divides the order of G. In other words, for any element X that you take from the set X, its orbit, the order of its orbit will divide the order of the group G. Right. Okay. So first, we understand that we have a group G, which is acting on a set X, right? So for any element that you take from this set X, we can always find its orbit, right? And in that case, the order of that orbit, the number of elements in that orbit for this particular X is the same as the number of left cosets of its, the stabilizer of that element in G. Now, what we do is, we will define a function from to a particular element. Let's first of all fix an element X, right? And define a function phi from the set of left cosets of this stabilizer in G to X. And we define this by taking any left coset of the stabilizer and mapping it to G dot X, where dot resembles the group action. And over here, I have taken L stab X to be the set of all left cosets of stab X in G. Set of all left cosets of stab X in G. Right. Now, what are we going to do in this case? We are going to show that this function is a one, first of all, it's a well-defined function. That also we had to show. It's a well-defined function. It's one-to-one and it's onto the orbit of X, right? We will show that it's well-defined and one-to-one. Now observe, any left coset that you take will be mapped to G dot X, where X is fixed now. What sort of elements do we have in its orbit? The orbit of X contains every element G dot X, where G is taken over the group, right? So every any left coset will also be mapped to G dot X. So what we are going to do is we will show that this function is well defined one-to-one and onto the orbit of X. In that case, we can conclude, because it's one-to-one and onto the orbit of X, the number of elements in the set of all left cosets in G must equal the number of elements in the orbit of X. That's what is the number of elements over here is what we get as this index given above. Okay. So first we will show that phi is well defined. Defined as well as one-to-one, since we can prove this at the same time for any two elements that we take from L stab X. Let me take it to be G1 stabilize of X, comma G2 stab X, to be any two elements from this, taken from this domain. Then we have G1 stab X equals G2 step X if and only if G1 inverse G2 is an element in step X. Why do we have this? Remember, these are two left cosets. What you see over here is one left coset of step X in G by the element G1 on this side, and this left coset is equal to a left coset of step X in G by the element G2. And we know by a theorem that we went over, that we discussed when we were doing cosets, if two left cosets are equal, right, for the same subgroup of the same subgroup, then these the representatives that you have over here, G1, G2, these coefficients, we must have G1 inverse G2 to be an element in that subgroup, right? So we are simply utilizing that property. This is if and only if. Now this is an element in the group step X. By definition, because it's a definition, we can use the definitions are if and only if statements, right? Therefore, if this is an element in step X, we must have, by definition of the stabilizer of X, G1 inverse G2 dot X to equal X, because any element in this stabilizer must be fixing X. This is if and only if. By taking G1 on both sides, we have G1 dot G1 inverse G2 dot X equals G1 dot X. Now, this is a simple calculation what you see over here. From here, we can simply get G1 inverse dot G2 dot X equals G1 dot X. This is if and only if this is the G1 times G1 inverse gives you the identity. Identity times any element. By definition of group actions, you get that element. So we've got G2 dot X equals, oh, sorry, this is G1. G1 dot X. What does this give you? By definition of, let me go back. By definition of the function phi, G dot X is simply phi of G step X. So over here we have G2 dot X. By definition of this function, we have this to be phi of G2 step X equal phi of G1 step X. Exactly what we wanted to show. So we see that this function is, if you consider the forward direction well defined, the other direction 1 to 1. Right? So we, at the same time, we have shown that this is well defined as well as 1 to 1. Now let's find, to show that phi is onto the orbit of X, it's an onto function. When you restrict, oh, sorry, when you restrict this codomain, to the orbit of X, what you get as phi, but what you have phi is to be an onto function. So in order to show that, what we're going to do is we will show that the image of phi is actually the orbit of X. Now observe that the image of the function phi is simply phi of G step X, right? Where G step X, by definition of the image, this is taken from the domain L step X, right? Now, phi of G step X is simply G dot X, where G over here comes from G. By definition, what is this function? Simply the orbit of X. So now we see that phi is a 1 to 1 P is 1 to 1 and on to all X. So we have the number of elements in the codomain, sorry, the number of elements in the domain to equal the number of elements in the range, which is the orb X, right? And what do we have over here as the number of elements in the domain? The number of left cosets of step X in G. Number of distinct left cosets of step X in G. In other words, that index that we listed above, right? Therefore, the index which gives you this value, the number of distinct left cosets of step X in G is equal to the number of elements in this orbit. Okay, now on the other hand, if G is finite, what do we know? If G is finite, we know that this index is simply equal to what? Order of G divided by order of step X. How do we know this? We actually know this from the proof of the Lagrange's theorem, because the stabilizer of X is a subgroup of G, right? So when G is finite, we know this index to equal the order of G divided by the order of the stabilizer of X. Therefore, we know that the order of this orbit is equal to this index, which is equal to this. So from this, we can simply write the order of G as a multiple of the order of, the order of the orbit of X. In other words, the order of the orbit of this element divides the order of G. Okay. Do you have any questions? So now we know that when a group G acts on a set X, you can take any element, find its orbit, find its stabilizer. The order of the orbit of that element, or the number of elements that are in the orbit of that element, is simply the index G, simply the same number of left cosets of the stabilizer in G of that element. Okay. Now, when G is finite, there is a way for us to find the number of elements in the orbit by simply taking the order of G, the quotient, the order of G over the order of the stabilizer of the same element. Okay, now we have a simple proposition. Okay, let G act on X, or X be a G set. Then the first property is X and Y are in the same orbit. If and only if X equals G dot Y for some element G in the group. In particular, if for any given x, y elements that you take from the set X, there is some G in the group such that X is equal to G dot Y, then there is only one orbit, one distinct orbit in this entire set X. So this orbit will contain all of X, is only one orbit. Now observe, let me write, no, before we get to the second statement of the proposition, another statement. If you go over the first sentence over here, X and Y are in the same orbit if and only if X is equal to G dot Y for some G. So in the second statement, it says, in particular, if for any given X and Y, there is some G such that X is equal to G dot Y, then there is only one orbit in X. Over here, we are picking certain X and Y. There is a certain X and a particular Y. For those two to be in the same orbit, we only need one G satisfying this equation. And if for any given, you take any two elements in X, any two distinct element or distinct or identical, doesn't really matter. Any two elements that you take from the set, if you can find at least one G satisfying this, then that means every element must be in the same orbit, right? That is the difference. Over here, you are picking two particular elements to be in the same orbit. And in the second sentence, you're saying that if this is true for any pair of elements that you pick, then we must have only one orbit. Let me write the second statement also, then go to the proof. We have the stabilizer of G dot X. Now observe, G dot X is an element in the set X is equal to G stab X G inverse. Right? In particular, stabilizers of elements in a common orbit are conjugate. What does that mean? This means, I'll just put over here, that is, if you have X and Y to be in the same orbit, then there exists G in the group such that the stabilizer of X is simply G times stab Y G inverse, right? So the stabilizers are conjugate. Okay, let's get to the proof. Right, so the first one is we have to show that if two elements belong in the same orbit, then we must show that there is at least one G such that X is equal to G dot Y. And if there exists some G satisfying that equation, then those two must belong in the same orbit. So it's an if and only if statement. Let's take x and y to belong in the same orbit. Let's take the orbit of the element z. Suppose x and y are two elements in the same orbit. Then, by definition of the orbit, right, what sort of elements does it contain? This contains all elements g dot z, where g comes from g. Now, x and y are elements in this orbit. Then, for some g1, g2, x must equal g1z, y must equal g2z. These two elements must take the form of g dot z for some g, right? So, let's write then there exists g1, g2 elements in this group such that x is equal to g1 dot z and y is equal to g2 dot z, right? So with this, let's go to the first one. We have x equals g1 dot z. What I'm going to do is I will take g1 inverse dot on both sides. Right, and this implies we have from here the right hand side of the equation would simply amount to being z. The left hand side would simply be g1 inverse dot x. So we have g1 inverse dot x equal z, and y is taken to be g2 dot z. Okay, what we are going to do is this z that you see over here, y equals, now we want to find some g such that g dot x is equal to y. We are in the process of doing that. Y is equal to g dot z. Z we have from here to be g1 inverse dot x. So what I'm going to do is replace it by that element. This implies that y is equal to g2 g1 inverse dot x, right? So then what do we have over here? G2 times G1 inverse, an element in G, because G1, G2, they are both elements in the group G. G2, G1 inverse is also an element in G. We have gotten exactly what we wanted. So then there exists, if I simply replace G1, G2 inverse by G, we can say there exists G in G such that y is equal to G dot x. Right. Now suppose on the other hand, there is some g such that y is equal to, now to prove the other direction, now suppose y is equal to, let's say, g naught dot x for some g naught in g, right? Now, for some g naught in g, let's find the orbit of x. By definition, this is all elements g dot x, where g runs over the group G, or we take all elements in G and take the action on x by all these elements, right? This implies that g naught dot x is an element in the orbit of x, because the orbit of x contains g dot x for every g. G naught is some element in the group. Therefore, g naught dot x must also be in the orbit of x. And what do we have as g naught dot x? This is simply equal to y. Y then must be in the orbit of x, right? And not only that, now y is in the orbit of x. X is also in its own orbit. Why do we have that? Since X can be written as E dot X and the identity is also an element in the group, this belongs in the orbit of X as well, right? This is the identity and element in G, right? So we have X and Y both to be elements in the orbit of X. Okay. Now, on the other hand, if for any two elements X and Y you pick, there exists some G, right? We must have X and Y to be in the same orbit by what we just proved, right? And because this property holds for any X and Y, every X and Y must be in that same orbit. That means every element that you take from this set will go in this orbit. So the full set is in the orbit. There is only one orbit. There can only be one orbit. So we can simply argue and write now if for any xy in X, there exists some G in G such that X is equal to G dot Y. We must have X and Y in the same orbit. This is by what we just proved now. By what we just proved. Must be in the same orbit. Now, this property holds for every X and Y. Since this holds X and Y, all X and Y must be in the same orbit. In other words, all of X must be in this orbit. What does it mean? There is only one orbit. Okay. Now to prove the other one. Okay. Do you have any questions from what we just finished?
No, madam.
Right. Now, first we will show that the stabilizer of G dot X can be written as G stab X times G inverse. In particular, stabilizers of elements that are in a common orbit, are conjugates. So you take any two elements in the same orbit, the stabilizers must be conjugate. Okay. The proof of the second one. First, let me write down as a reminder the definition of the stabilizer. You take all elements in G, the stabilizer of the element X is elements in G that fixes X, this element X, through the group action. Now let's find step G dot X, simply using this definition. This gives you, because we have G over here as well, I will simply take this to be G naught, right? Because we don't want to confuse ourselves. Okay. All G naught in G such that G naught dot this element, G dot X. Remember, G dot X is an element in X, is equal to G dot X. This is equal to every G naught in G such that if you use the second condition of a group action over here, we see that this is simply G naught G dot x equal g dot x. Now what do? We want to show that this stabilizer of g dot x is simply g times stab x times g inverse, right? Okay. This contains all elements g naught in G such that by taking G inverse on both sides, we see that this is G inverse dot G naught G dot X equals G inverse dot G dot X. And this further simplifies to G inverse G naught dot x equals G inverse G is the identity dot x is simply x. So we will write x. Right? What I'm going to do is I will write in another one. Take K to be the element G inverse G naught G, which is an element in G. Right? Then we have, because K is equal to G inverse G naught G, G naught is by simply taking by taking the product of G on the left, G inverse on the right of this equation, we see that G naught is G, K, G inverse, right? Therefore, this is equal to G naught, I will replace by G, K, G inverse, where K dot X is equal to X. What do we have over here? K dot X equals X. So K fixes X. K belongs in the stabilizer of X, in other words. So what you have over here is G times any element in the stabilizer. So stab X times G inverse. Right? Is it clear? For example, if I write this separately, if I write this set, stab X, G inverse. How do we define this set? It contains elements of the form G, K, G inverse, where K comes from stab X. In other words, G, K, G inverse. If K comes from stab X, by definition, we must have K dot X to equal X. Exactly what we see over here. Right? That's why from here, I simply concluded this set to be G stab X, G inverse. Any questions? Do you need to make any clarifications before we move on?
No, madam.
Right. Now, on the other hand, if you have two elements that are in the same orbit, right? Let's say if X and Y are in the same orbit, then we must have G dot X to equal Y from the proof of the first one, right? In the proposition for some G. For some element that you take from this group. Then, and from what we've just proved, we have step of G dot X to equal what? G step X, G inverse. So G dot X is what in this case? This is equal to Y. Step Y is simply equal to G step X, G inverse. This is for some G that you take from the group. Okay, any question?
No, madam.
Right. Then, right. Okay, let's go over some definitions and get back to examples. We want to know what fixed elements are and all that. Okay. Mm, Let me give you this definition first. We say that the group action, I think I gave this one early on. We say that the group action of G on X is transitive if there is only one orbit, right? So let me write the group action is said to be transitive if X contains only one orbit, right? In other words, uh, the action because it's a definition, this is an if and only if statement, if and only if. There is another way to, by simply going over the preposition earlier, we can sort of reformulate the same definition and write the action is transitive if and only if X contains only one orbit, or in other words, for any two elements, X and Y, in X, there exists some element G such that X is equal to G dot Y. Right? X is equal to G dot Y. Now the other definition, an element is said to be fixed. Now let me formally write it. An element, even though we went over this definition, we never formally wrote it. An element X in X is said to be fixed by the action of G on X if G dot X equals X for all G in G. Now earlier, when we were talking about, or when we were defining the stabilizer, we considered all elements in G that fixes X. That means first, there are some G's, some elements in the group that fixes X. You take some, for example, the identity. Identity actually fixes every element. Identity fixes every element. So you take a particular X, you take identity dot X will always equal X. If for some other G also you have that G dot X equals X, we say that that element in the group fixes the element X. But in this definition, we say that an element is fixed by the action. If this condition, if this equation holds for every element that you take from the group, if every element in G fixes that element, we say that the element is fixed. Okay. So let me write. X in X is fixed by the action of G if orbit of X contains only the element X. Why is that? Why do we have that? If you look at the orbit of X is defined to be all elements G dot X, which are in the set X, where G comes from G. Now say X is fixed, right? If X is fixed by the action, then G dot X will simply equal to X for any G that you take from the group, right? If X is fixed, G dot X will always simply be X for any element that you take from the group. So how many elements are there in this set of X? It will simply contain X because no matter which G you pick, G dot X will always end up being X. So the orbit in this case would be the singleton set containing this particular element X. Okay. Now we define the center of the group and the normalize. Okay. Center of G. We define this to be ZG. This is given by all elements X in G such that Gx equals Xg for all G in G, right? And this is a normal subgroup of G. Actually, we have, even though I never gave that specific name center of G, we have shown that for any group G, this given set is a subgroup, right? This given set is a subgroup. So if you, it's not just a subgroup, it's a normal subgroup. X in G, when you take G inverse on the right on both sides, we see that we can simply write this as Gx G inverse equals X for all G in G. If you look at this element, this is conjugation, right? So what we are simply looking at is the group action on the group itself by conjugation. Okay, this is what we define as the center of the group G. Okay, so let's go over some examples to understand more about the about an element being fixed by the action, the center, the stabilizers, orbits, and all that. I shouldn't say more examples. We're sort of going to look at the same examples. Let me say going back to examples. Okay, first one, these are some of the major groups. Let's take when G acts on itself by left multiplication. We have seen that this is indeed a group action, right? The action on the group by itself. When G acts on itself by left multiplication. Right? So for your reference, this would simply be from G cross G to G defined by P of G1 x, or maybe simply doesn't matter. This given by G1 times x. Okay. Okay. First, let's find the orbit of the identity. I want to show that there is only one orbit. So if the entire set belongs in, if all elements in the set, so our set in this case is the group G. If all elements in this group belongs in that one orbit, right? Then there is only one orbit for this section. There is only one orbit for this set. Observe that observe that the orbit of the identity is given by what? G dot E, where G is in G is in the group. G dot E is simply G, because now we are taking the group action. Now G acts on itself by left multiplication. So G dot E is simply equal to G times E, which is G by definition of the identity. What do we have over here? G, where G comes from? The entire group G. The entire group G. So all of G belongs in this one orbit. Therefore, there is only one orbit. There is only one orbit, which is orbit of E. By taking the identity, we can see this clearly, that we get the entire group. So what can you say about the group action? Group action is, by definition, transitive, because there is only one orbit. The group action is transitive. Okay. Now, for any x that you take from the group, let's find the stabilizer. For any x this is, right? What do we have as the stabilizer? The stabilizer gives you every element in the group that fixes this particular x. G dot x equals x. What do we get from G dot x? Simply the left multiplication G times x, which is equal to x. Now what do? We take x inverse on both sides on the right. So we have gx times x inverse, x inverse. We have every element g in G such that x times x inverse is simply the identity. G times the identity is G equals x times x inverse is simply the identity. So what does this set contain? Every element in G such that G is equal to the identity. In other words, simply the identity. Now X is chosen arbitrarily from the group. So for any element, the stabilizer will always end up being this trivial subgroup of G. The trivial subgroup of G. The subgroup containing only the identity. Okay. So in other words, this any element that you take from this group, the set, will only be fixed by the identity. No other element. Not by any other element. Okay, let's take a look at another example. Okay, let's take the second one. When G acts on itself by conjugation. Just to remind you, this is the now group G is acting on itself where phi of gx, which we define by g dot x, given by gx g inverse, acting on itself by conjugation. Okay, let's take any element x in G and let's find its orbit. Okay, this is given by G dot x for every G that you take from the group. G dot x is simply gxg inverse, where G comes from G. Now this orbit has a special name. This is what we call, for this particular action, the G acting on itself by conjugation, the orbit of X is called the conjugacy class of X. Conjugacy class of X. Now let's find the stabilizer of this element. If we find stab X, this is given by all elements of G which fixes X. G dot X equal X. And if we replace G dot X by GXG inverse, we have this GXG inverse equals X. This is equal to what? G in G, such that by taking G of this equation on the right, on both sides, we see that Gx is equal to Xg. This also has a special name. This is what we call the centralizer of X. Centralizer of X, right? Now, what is the difference between this and the center of G? I'll write it and I'll show you. Again, if we go back. As the center of G, what do? We take every element in the group such that Gx is equal to Xg for every other element in the group, right? So in this case, we simply take elements in G that fixes this element, not elements in G that are fixed by every element in the group. Okay? Right. Okay, so this is what we call the centralizer of X. Okay. Okay, let's go to the center of G in this case. We know that Z of G is defined to be all elements X in G such that for all G in G, we have Gx equals Xg. Gx equals Xg. And we know that this is a subgroup of G. It's a normal subgroup of G. Right? Okay. Now, let's take a look at the fixed points, right? X is a fixed point, fixed by the action, right? X is a fixed point or is fixed by the action if and only if, by definition, G dot X is equal to X for all G that you take from the group. This is if and only if, by definition of the group action, G dot X we write as Gx G inverse equals X for all G in G. Now we somewhat simplify by multiplying both sides on the left by G. to write Gx equals Xg for all G in G. Right? This is if and only if. If you look at the definition of the center of G, we see this contains every X such that for any other element that you take from the group G, Gx is equal to Xg. In other words, by definition of the center, this means X belongs in the center of G. In other words, what does it mean? When G acts on itself by conjugation, the center consists of all the fixed points. When it's a fixed point, it belongs in the center. If it's a point in the center, it is a fixed point. So we simply write the center consists all the fixed points. Okay. Now, then we have the other group action. When G acts on itself, when G acts on the set of left cosets, which we started off with the group action. Let's go over that one. Let's take G to be a group, H a subgroup of G, and let's LH denote, let's denote by LH the set of left cosets of H in G. Right? Now, let's consider when G acts on LH by left multiplication. When it acts on left multiplication. So how do we define this? You have P from G cross LH to LH, where phi G comma XH denoted by G dot XH is simply given by GXH. This means the left coset of H in G by the element G times X. Right. First of all, let's find the orbit of the identity element in here. Or let's not say the identity element. Let's simply say the orbit by H. H is also an element in LH. H, which is simply the identity element times H, is an element in this. H is a left coset of itself, right? So let's find the orbit of H. By definition, this contains all elements G dot H, where G comes from the group. This is equal to G dot H is simply given by GH, really. If you want to see this, I will replace H by EH, then write this as EH, where G comes from G. This is simply GE by this action of H, where G comes from G. G times the identity is simply G, H, where G comes from G. By definition, this is LH, all the left cosets of H in G by elements in G, right? So all of the elements that are in LH belongs in this one orbit. What does it say? It says we only have one orbit so that the group action is actually transitive. Right. Now let's take any element x from G and find the stabilizer of, and then when you take an element x from G, we have xh, the left coset of h by the element x, to be an element in this set, LH, right? Now let's find the stabilizer of XH. This is equal to, by definition, every element in G that fixes this element by this group action, G dot XH equals XH. And let me replace, we know that G dot XH simply gives you this left multiplication, GXH equals XH. Now you have two cosets that are equal to each other. We know if you have two left cosets, let me write it down over here. We use the same property when you have G1H equals G2H. This implies G1, G2 inverse is in H. That is exactly what we are using over here, right? So we take G in G because these two are the same. This means I will simply write this element X inverse Gx is in H. Okay. This is equal to G in G such that G is actually in X, H, X inverse. If you have X inverse Gx to be an element in H, this means G must be an element in X, H, X inverse. You can see this. So we can conclude that this set, G in G, where G comes from this set. So this entire set contains elements from the set X, H, X inverse. To see that why we have this, when X inverse Gx is an element in H, this is if and only if X inverse Gx is equal to H, where H comes from the set H. This is if and only if G, by definition of sets, okay? We are simply applying the definition of the set H. If it is an element in H, it must take the form of an element that's in the set. So G, by taking in the equation, we take the left multiplication by X, right multiplication by X inverse to see that G is in fact XH, X inverse, where H is an element in H. What does it mean? G is an element in XH, X inverse. This is why we simply come from here to here. So we see that the stabilizer of XH is equal to XH, X inverse, the set. Right. Now, to see what sort of fixed points we have, AH, which is an element in LH, is a fixed point if and only if G dot AH is equal to AH for all G that you take from this group. This is if and only if, by simply applying the definition of this group action, we have GAH to equal AH for all G in G. Now, once again, we have two left cosets that are equal to each other. So we know that, once again, applying that property, this implies A inverse, it's an if and only if statement, by the way, A inverse GA is an element in H for all G in G. This implies, once again, we can say G is an element in AHA inverse for all G in G, right? So every element in G is an element in AHA inverse. So what does it say? This says the group G is a subgroup or a subset of AHA inverse. But we know that when H is a subgroup, this set must be a subset of G. So our only possibility is that G is equal to A inverse. Because from this right, the statement that we just wrote, G is an element in AHA inverse for every G, means that G must be a subset of this. But G is the bigger group. We know AHA inverse will always be a subgroup of G. Therefore, the only option is G at this point for G to be equal to this set, right? So let me write it as since AHA inverse is always a subgroup of G. Now what do? We take multiplication by A inverse on the left, A by A on the right, to see that A inverse GA is equal to H, right? Now this tells you that G is equal to H. Why is that? This A inverse, they are all elements in G. They are all elements in G, right? So when you write A inverse GA, by definition, this contains elements of the form A inverse GA, where G comes from G. Now observe, A and A inverse are also elements in G. So what you see over here is G naught. This is an element in G, where G naught is an element in G. So by definition, this is the entire group G. So I will replace this by G. There simply this A inverse A will gets absorbed into the group G because there are elements in that group. So we see that G is equal to H. So AH is a fixed point if and only if H is equal to G. Okay. And it's easy to see that this is a subgroup. I will leave that to you as an exercise. Prove that this is a subgroup. When H is a subgroup of G, this implies GHG inverse to be a subgroup of G for any G that you take from the group. Right? Okay. Any questions?
No, madam.
Right. Okay, one more definition we'll do. Let H be a subgroup of G. The normalize of H in G. The normalize of H in G is defined to be the subset denoted by N of H, G in G such that GHG inverse is equal to H. GHG inverse is equal to H. This is the normalize of H in G. Now we can see that, or we can prove that Okay, so we can show that the normalizer is a subgroup of G. Let me state this as a theorem. Hmm. Let X be the set of all subgroups of a group G. So X contains all subgroups of a group G, and we let G act on X by conjugation. Act on X by conjugation. What does it mean? Uh, we have phi from G cross X to X defined by phi of Gx to be, I'll write GH by, because X contains all subgroups of G. So H is a subgroup of G, which is an element in X. This will simply be G dot H. Now the action is conjugation. So this will be given by GH, G inverse. Right? Then for any H element in X, when you take an element from X, because X contains all subgroups, we know that this is a subgroup of G. The stabilizer of H is simply equal to its normalizer in G. In particular, this is a subgroup of G. Furthermore, the fixed points are the normal subgroups of G. Fixed points are the normal subgroups of G. Okay. First, we have to show that the stabilizer, take for any H an element in X. We know that H is a subgroup of G. We have to show that the stabilizer of H is the normalizer of H in G. So let's, by definition, write stabilizer of H. Every element in G that fixes this particular element H. This is equal to, by definition of the group action, this is simply G inverse, which is equal to H, right? By definition, if you go back to the definition of a normalizer here, every element in G is such that G inverse is equal to H. So by definition, this is the normalizer of H in G, right? Now in our next step here, show that the normalizer is actually a subgroup of G. So let me write, need to prove that. So let G1, G2 be elements in this normalizer. Right, first of all, we have to show that this is not empty. We can see that the identity element is in there. Why is that? Let me write, observe that. The identity is in the normalizer of H, since EHE inverse is equal to H. Why is that? The identity is an element in H. So when you take identity H, the inverse of it gets absorbed into H. This is equal to H. So that normalizer is not empty. Now we take any two elements G1, G2 from the normalizer fetch. By definition, we have G1H, G1 inverse to equal H, which would imply when you take left multiplication by G1 inverse, right multiplication by G1, which would imply this equals G1 inverse H, G1, right? And because G2 is also in the normalizer, we've got G2H, G2 inverse to equal H. Now we have to show that G1, G2 inverse is in H, right? G1, G2 inverse is in H. And this also implies that H is equal to G2 inverse H, G2, right? Let's calculate G1, G2 inverse times H, G1, G2 inverse. The inverse of this. If this ends up being equal to H, by definition of the normalizer, G1, G2 inverse must belong in the normalizer of H. So this is equal to G1, G2 inverse H. When you take the inverse over here, we have the inverse of the inverse, G2 inverse of the inverse, which is G2, G1 inverse. Now, using the associativity property, from here we know that G2 inverse H, G2 ends up being H, G1 H, G1 inverse. Once again from here, this equals H. What does it say? By definition, G1, G2 inverse must belong in NH. And so, by the subgroup criterion, we must have NH to be a subgroup of G. Right. And we have to show furthermore that the fixed points are normal subgroups of G. So now H, that is an element in X, is a fixed point if and only if this is fixed by the group action, right? G dot H is equal to H for all G in G. If and only if, by definition of the group action, this is G H G inverse equals H for all G in G. And we know that this simply means, by definition of a normal subgroup, H is a normal subgroup of G. We have done certain equivalent statements for a normal subgroup in a group. Referring to that, we conclude with this condition that H is a normal subgroup of G, right? Therefore, fixed points are normal subgroups of G. That's the end of this proof.